For each observation, calculate the rate at which temperature changes as altitude changes in degrees Celsius per kilometer. Predict what the temperature would be if the scientist went from his lab to an altitude of 4.4 kilometers, and explain. So some of the chart is already filled out for us. So if we look at the start and the end altitude and then its change, we can fill in the table by counting. So it's a positive 4/10 of a change, positive 1 and 71 hundredths of a change. Here we went negative 2/10 because if we start at 1/10 and we go to negative 1/10 on the number line, we've gone a distance of negative 2/10. Similarly, negative 4/10 and then the last one a positive 2 and 4/10. We can find the change in temperature by following the same idea. So we fell 2.5 degrees. We fell 10.1 degrees. We gained 1 and 2/10 degrees. We gained 2 and 7/10 of a degree, and then we fell 14 and 9/10 of a degree. We then can identify the rate of change per kilometer with division. So the change of temperature divided by the change in altitude, which gives us these changes. So -6 and 25 hundredths, -6 and 4/10, -6, -6 and 75 hundredths, and -6 and 2/10. So although the changes seemed kind of drastic and all around, our rate of change is very similar. Our prediction, if an altitude of 4.4 kilometers, and explain. So our starting altitude has been the same and our altitude of 4 and 4/10 is listed. So its change would be to add 4 and 3/10 of a change. So now we can identify what the average rate of change is for the temperature. So we can add them all up and divide by 5 because that's how many there are. So the rate of change per kilometer average is -6 and 32 hundredths. We could figure out the temperature change by taking -6 and 32 hundredths, multiplying it by 4 and 3/10, so going the opposite of how we found them, so reversing the rules. So for an end change of -27 and 2/10. So then we can find the starting temperature or the ending temperature by taking -27 and 2/10 and adding 20 to get an ending temperature of -7 and 2/10. The same pattern exists when we use multiplication and division with negative numbers. Some homework. Raina learned that in order to change a fraction to a decimal, she can use the standard division algorithm and divide the numerator by the denominator. She noticed that for some fractions like 1/4 and 1/100th, the algorithm terminates at the hundredths place. For other fractions like 1/8, she needed to go to the thousandths place before the remainder disappears. For other fractions like 1/3 and 1/6, the decimal does not terminate. Raina wonders which fractions have terminating decimals and how she can tell how many decimal places they have. Convert each of the following unit fractions to decimals using the standard division algorithm to help Raina look for patterns with her decimal conversions. Which fractions on the list have terminating decimals, decimals that eventually end in zeros? What do the denominators have in common? Which fractions on the list have repeating decimals? What do those denominators have in common? Which fractions in reduced form, and PQ just is a standard form, a generic form of writing a fraction, which fractions do you think have terminating decimal representations, and which do you think have repeating decimal representations? Scan and upload your documents and reasoning to the decimal expansion discussion board. then respond to 2 classmates' thoughts and ideas of their observations. The other part of your homework is to print the homework file included in the practice problems homework Dropbox. Complete the problems as outlined within the homework pages, taking care to show all your work. Scan and upload your documents back into the practice problems Dropbox.